So we were asked the question on the homework. This is the optional question of whether there is a tie game in 4-dimensional tic-tac-toe. The answer to the 3-dimensional tic-tac-toe is in the book, and yes, there is an example of a tie game. And when I give you this result, I don't know the answer. I don't know the answer. So I'm going to be surprised if there isn't. I think it would be hard to prove that there isn't a there isn't a tie game. Wouldn't that be difficult? You would literally have to go through all of the combinatorics of the X's and zeros and show that they all had a winning game in them.
Yeah, you'd have to find some math proof behind it, since one counterexample disproves.
Yes, yes, but if there is a tie game, all you have to do is give one example of a tie game, and that would do it, right?
Mm-hmm.
Okay. Okay, well, good. Yeah, there was also a question about finding the Fourier transform of the hexagon, of regular hexagon. That also is a difficult problem. Chris mentioned the idea of finding the Fourier transform of a triangle and then rotating that triangle 6 times in order to form the hexagon, and certainly that would work. Another way is to find a parallelogram. You'll notice that the hexagon has a composition of 3 parallelograms. Each parallelogram is the conjoinment of 2 equilateral triangles, one of them flipped over. And that's a possibility also. I've seen those 2 approaches used. Neither one of them turns out to be very pretty. But if you do that, that will be the hink, right? Fourier transform of a hexagon is a hink. Fourier transform of a circle is a jink, and the Fourier transform of a square is a sink. So we have sinks, jinks, and hinks. Okay. Any other questions about the homework?
Yeah. Let's see. I was wondering what the let's see, like how the rectangle is turned into a jink. I guess the fine details, because
Wait, what do you mean the rectangle turns into a jink?
I mean, it being transformed. Yeah, pi of r.
Okay, that's pi of r. That's actually a circle. That's not a rectangle.
Okay, sorry, I was looking at it from level ground.
Right. Yeah, pi of r is a circle of unit diameter, and that's in a radial coordinates, and therefore it's the Fourier transform of a circle, which we know is a jink. We worked that out as our first, I believe, our first or second Hankel transform.
Okay.
Okay, with that in mind, let me go ahead and share my screen. Let me prepare for my magic on-screen writer here. So last time we were together, we were finishing up some of the ideas of the Fourier transform, and this is very interesting because we found out that the phase in the Fourier transform contained more information, at least in this little example here, that we had more information in the phase than we did with the corresponding magnitude. This was important in terms of early days of pattern recognition. We used to have, for example, we could take a tank, right? This is my idea of a tank. Well, we know that the tank, if this was some image, would have a corresponding Fourier transform of big X. And that's all well and good. So the question is, what happened if we shift the tank? What happened if we shifted the tank, for example, to be up here and we were doing pattern recognition, trying to figure out whether it was a tank? Well, if this is X with a shift in it, this would Fourier transforms to X to the EJ shift, right? That's what that would correspond to. But you notice this has the same Fourier transform as this. So in the early days, they used to think that, well, let's use the magnitude of the Fourier transform as the template to get tanks. But there's a problem. And the problem is that what about if you have a tank from a different perspective? What happens if you have something like this, right? So you have a scaled tank. You still want to recognize the tank. So this would be X scaled. And well, what do you do here? How do you mess around with this? Well, it turns out there's a transform, a different transform called the Melon Transform, which is in your book, but we're not going to go over it. But the Melon Transform turns out to be invariant to shift. I'm sorry, to scale. So you could use the Melon Transform as invariant. And then guess what else you had to do? You had to do the scale, and then you had to do the rotate. What happens if you rotated the tank? Okay, so this would be X rotated. Well, there's ways to do that, and this would be something using for circular harmonics. And that's in the book, but we're not going to cover it. But both of these cases, both the Melon Transform and the circular harmonics, what you had to do is you had to throw away the magnitude. So you just looked at the Fourier transform of the Melon Transform. You just looked at the magnitude of the circular harmonics. And as we saw over here, this is really bad because a lot of that information on the tanks is included in the phase. And if one tries to, what they found out is that if they tried to apply all of these things together, then there would be a problem. And that problem was that pretty soon everything looked like a tank. Everything looked like a tank that was scaled or rotated or something like that. So it wasn't very good. And one of the reasons that it was no good was because it threw away the phase of what was going on. So the phase is very, very important in these situations. So how would you do that today? Probably with using something like a deep convolutional neural network, correct? You could train a deep convolutional neural network and use AI sort of pattern recognition in order to detect tanks, to see if there was a tank in the scene or not. But there was a problem with this also. It's detailed in my book, A Case for Killer Robots. There was an example of deep convolutional neural networks that were trained with let's see, they were trained with American tanks. No, they were trained with pictures with tanks and pictures without tanks. And so they wanted to train a neural network in some sort of different scenarios, whether there was a tank present or whether there wasn't a tank present, and they got really, really good performance on the neural network. But when they applied forensics to it, they found out that all the pictures without tanks were taken in the evening, and all of the ones taken with tanks were taken during the day. And the neural network was not learning on the tanks, it was learning on the background illumination and whether the sun was shining or whether it was evening. So yeah, totally different. That's a big problem, of course, with neural networks and computational intelligence in general. But nevertheless, this is a little bit of background, and you can see why, when one looks at the phase contribution to the overall image, you can see why this indeed failed. So let's go into now the two-dimensional sampling theorem. If you recall, in one dimension, the Fourier series was the Fourier dual of the sampling theorem, or vice versa. The sampling theorem was the Fourier dual of the Fourier series. And so we already have a background in the Fourier series from our previous lectures, so we're going to use that in order to derive the Fourier transform in higher dimensions. In order to do that, it's important to see how sampling geometry replicates into periodicity. And this is manifest in something called the multidimensional comb theorem. And we have here, first of all, we have Q, which is a sampling matrix. So Q in the T1, T2 domain, this could be an image domain. This could be X and Y, for example. We just use T1 and T2 as because in one dimension, we usually think of time. But you notice that there is a periodicity matrix here, correct? There's a periodicity matrix. And this periodicity matrix, what we're going to do is we're going to put Dirac deltas everywhere. And we're going to put them there in accordance to a sampling matrix of Q. Then we're going to generate P, which is Q inverse transpose. And this P is going to correspond to another set of delta functions here. Do you remember in one dimension a comb Fourier transformed into a comb, right? In two dimensions, a periodic replication of Dirac deltas in the time domain corresponds to a periodic replication of Dirac deltas in the frequency domain. So this is kind of a result where you look at it and you say, yeah, I think I can see that a comb Fourier transforms to a comb. So a bunch of Dirac deltas over here should form to a bunch of Dirac deltas over here. And here is the relationship. The relationship is that the Dirac deltas in the frequency domain have, if you will, a periodicity matrix of P, which is equal to Q inverse transpose. So it turns out that for this replication, this hexagonal replication, that the Fourier transform corresponds to a periodic replication here, which is also hexagonal. But you'll notice that they're a little bit different. Here, the hexagon has the pointy side on the top, doesn't it? Right? You see the pointy sides on the top? Over here, when we do the Fourier transform, where is the pointy part? The pointy part is on the right and the left. So they're hexagons, but they're a little bit flipped. They're a little bit flipped. And so this is fundamental for understanding the sampling theorem, that the Fourier transform of a periodic replication of Dirac deltas Fourier transforms into two dimensions into a periodic replication of delta functions in the frequency domain. Now you've noticed that I have made this representation here in terms of two dimensions, but you will notice that the equation here is applicable in n dimensions, okay? It's applicable in any dimension that you want to. There's a proof of the multidimensional comb lemma in the book. So here we're going to go through the heuristic example of the sampling theorem in two dimensions. Okay, this parallels the derivation that we had in one dimension, which was very intuitive, very geometrically obvious. Here we have a two-dimensional function. This is our x of t. It's x of t1, t2. We are going to assume that it is band limited. What does it mean band limited? It means it's zero outside of say a finite dimensional box. If it's zero outside of a finite dimensional box, we say that it's band limited. Is that okay? So now what we're going to do is we're going to take this image and we're going to multiply it by the Dirac deltas here. So this is just a sequence of Dirac deltas. And when we multiply by the Dirac deltas, that's going to give us a a raster scan, and each one of these points now is going to be weighted by the value of the image. So whatever the value of the image here, that's going to be the area under the Dirac delta here. So you can see all of these delta functions are not equally shaded, are they? There's some that are lighter than other ones, corresponding to stronger and weaker Dirac deltas, and that's weighted by the corresponding function up here. Does that make sense? And this is very intuitive, right? We take an image, we multiply it by a sequence of Dirac deltas, and we get we call it a sample, the signal of samples. Okay, that's S of t. That's the signal of samples. Well, this is very intuitive. What is not as intuitive is what happens in the frequency domain. In the frequency domain, we take the one-dimensional spectrum, and of course we've just determined that this two-dimensional array of Dirac deltas corresponds to a two-dimensional array of Dirac deltas over here, correct? And what happens if you multiply in the time domain? If you multiply in the time domain, what do you do here? You convolve, don't you? So when you convolve something with a delta function, you get the thing back where the delta function is centered, correct? So what we get is this spectrum, and now it's replicated everywhere where there was a Dirac delta happening. And I think you can see the phenomena of aliasing here too. What happens if we make this sampling too coarse? If the sampling is too coarse, these Dirac deltas are going to be close together, and these spectra are going to overlap, won't they? These spectra are going to overlap. So we better make this such that the replication of the spectra don't overlap. Otherwise, we have aliasing. So in summary, we sample in one domain, we replicate in the other domain. And the signal of samples, S of t, has a Fourier transform, which is, the replication of the spectrum. Now notice the Fourier dual here. This is a Fourier series, right? You can think, well, this is a periodic function, correct? We can look at this periodic function as we can do the Fourier series of those, correct? We can do the Fourier series of the periodic function. And it turns out that these weighted values are indeed the Fourier series coefficients. So if that helps, great. If it doesn't help, that's fine. Just pointing out the Fourier dual. So that's what happens. And now the question is how do we replicate, how do we generate the original signal from these samples? And that's shown over here. What I've done is I've replicated this figure up here. These two figures are exactly the same. Now, over here, just like in the one-dimensional case, we did the intuitive operations in the time domain. Here, we're going to do the intuitive operations in the frequency domain and see what happens in the time domain. Okay? So let's go over here. We have these replicated versions of the spectrum. We're assuming that these replicated versions do not overlap. And how do we get this center one back? Well, we multiply the zeroth order spectrum. We multiply it by, say, a little rectangle here, or some sort of function that just allows us to get the zeroth order version back. We just want this one back, right? Because that's the spectrum of the original signal. So we multiply this by the rectangle, and then we obtain the original signal back, the spectrum of the original signal. That's very intuitive. And it's exactly what happens in one dimension. We've just extended it to two dimensions. Well, okay, we multiply here. So this times this rectangle is equal to the spectrum. We multiply in the frequency domain. What do we do in the time domain? We convolve, right? We convolve. and we will convolve with whatever the inverse Fourier transform of this guy is. In this case, it looks like the inverse Fourier transform is going to be the sinc of T1 times the sinc of T2 with some scaling factors, right? Because this is a pi. This is a pi in the one dimension and a pi in the second dimension, right? It's a separable function. So this thing's going to be a sinc in the one dimension, sinc in the two dimensions, times some constant out here. So whatever the inverse Fourier transform of this is going to be some sort of function here. Let's denote that function by a circle or two circles. So what does that mean? That means that everywhere there's a Dirac delta up here, that this interpolation function, and that's what this is. This is an interpolation function. Whatever this interpolation function is replicated at every point up here, isn't it? Now, in one dimension, what was that replication? In one dimension, when we had a bunch of samples, that interpolation function was a sinc, right? And we replicated at every point with the sinc. Now we have in two dimensions, so we have whatever that interpolation function is in two dimensions being replicated at every single point. And when we add up all of these little interpolation functions here, we have to get, in accordance to the analysis that we have here, we have to get back the original signal exactly. So does this make sense, at least in an intuitive geometric sense? I think just looking at pictures and applying basic Fourier transform theory allows us to kind of walk through this at a high level and understand what's going on. Again, if you're not sampling fast enough, if your samples are too far apart over here, what happens if you make these farther apart? If you make these farther apart, you make these samples closer together, don't you? That's the scaling theorem, right? You make it in time, you stretch it out. In the other domain, you push it together. And if the samples are too far apart, these are going to be too close together, and these spectra are going to overlap, and you're going to get aliasing in two dimensions. Any questions on this? On this intuitive kind of I hope it's intuitive sort of explanation of the sampling theorem in higher dimensions? Are you totally baffled, or do you understand? Or somewhere in between?
I'd say I understand.
Okay. Well, that's one vote. And as we learned in recent events, we can do a miracle and turn one vote into 1,000 votes, right? So let's move on.
Oh, I thought it was 150,000.
No, okay, no politics here. So this is the following example. This is a clean slate again. This is the same figure with the clean slate. I'm not sure why I did it twice. Now, let's look at some important parameters here if we understand that. One of the important parameters is the sample density. Now, we know about the sampling rate in the Nyquist rate. That's how many samples per second you have, right? And the samples per second is equal to 1 over twice the bandwidth of the signal, if you remember that. That's the Nyquist rate. Do you recall that? We actually went through an example with the sinusoid that we said that, well, the sampling rate had to be a little bit bigger than the twice the bandwidth. Remember, with the sinusoid and the Dirac deltas canceling out in a weird sort of fashion. But let's just say for purposes of discussion that we sample at twice the bandwidth. What is the corresponding sampling rate here? Well, let's look at the sampling matrix here. Once we sample this, notice that if we complete the parallelogram, we have one sample which is assigned to this tile, this kind of diamond-shaped tile. Do you agree with that? Here's another tile. We have one sample associated with this tile. We go down here, we have one sample associated with this tile. So what I'm trying to do is do a one-to-one mapping between the samples and the corresponding tiles. And you can see that we have what? One sample per tile, correct? We have one sample per tile. And what is a tile area? Do you remember we said that before? This area is
The
equal
determinant of the periodicity matrix.
Yes, I write faster than you talked. So yes, it's the determinant of Q. So we have one sample per tile. And so this is what this is saying down here. We have one sample per tile of area 1 over determinant of Q. What is the area? Say this is 2 dimensions and these are spatial dimensions, say in an image. This is x1 and x2, so they'd be measured in something like millimeters or something. What would be the units of this, of the determinant of Q?
Yeah, square millimeters.
Yeah, it'd be square millimeters. This is what you measure areas in a 2-dimensional plane, correct? You'll also notice that since P is equal to Q inverse transpose, I think it's pretty easy to show that the determinant of P is equal to 1 over the determinant of Q. Hopefully you've seen something like that before. So the sampling density is equal to 1 over the determinant of Q, which is equal to the determinant of P, correct? What is the determinant of P? The determinant of P is the area of a tile over here, right? And if T1 and T2 are measured in, say, distance, what's the units of U1 and U2? It's cycles per unit distance, cycles per millimeter, cycles per meter, cycles per millimeter, something of that sort. And so for U1 and U2, this is equal to cycles per millimeter squared. This reminds us of the 2-dimensional case. Remember reminds us of the 1-dimensional case. You remember in the 1-dimensional case where we went from minus B to B, what was the Nyquist rate? 2B. We must sample at 2B cycles per second. We have a similar beautiful thing here that we're sampling at not in the interval, but over a 2-dimensional area of the determinant of P, and this is going to be cycles per millimeter squared, for example. So therefore, in conclusion, that your sampling rate is going to be the determinant of P, correct? It's going to be determinant of the periodicity matrix that we have in the frequency domain. Now, if we would like to with the Nyquist rate, what are we doing? We're trying to minimize our number of samples that we have to store, correct? We're minimizing the number of samples that we have to store. If we want to minimize the number of samples that we want to store, what do we want to do to the determinant of P? We would like to make that as small as possible, right? And we would like to make that as small as possible under what constraint? That we don't have aliasing, that we don't have the overlap of these images here. We would like to make it as small as possible so that there's no overlap of the images, of the image replications. Because if there is overlap, you have aliasing, and that's no fun at all. Okay, any questions on this? The big takeaway here is that the sampling rate is equal to the determinant of P. That's the sampling, I'm sorry, not the sampling rate, it's the sampling density. It is how many samples that you have to take per, I did millimeter squared, but I think more generically we can say the samples per unit area.
Now, if we crammed the samples together in T1, but stretched them out in T2, would that what would that look like?
Well, again, if you stretch them out in T2 and you sampled at a lower sampling density, you put your spectra closer together, your replicated spectra closer together. And if you put them too close together, you get the overlap. So ideally, you'd like to put them together to the point where, I don't know, replicated spectra are just touching each other or something. Okay, any questions on this? Hopefully this is a nice generalization of your understanding of what happens in the one-dimensional or in the two-dimensional case. It's a generalization of the one dimension to the higher dimensional space. Now here is the sampling theorem, and let me tell you what this is. X of t is equal to the samples. These are the samples, x of q of m, times f sub c. Now this is the interpolation function. And recall, if we have in the U1 to U2 domain, if we have something like a tile, and this is the tile that we use to isolate the 0th order spectrum from all the replicated spectrum, then this is going to have a Fourier transform of f sub c of t. So f sub c of t has a Fourier transform of a rectangle function, which is 1 inside the tile, divided by the determinant of p. That's just a scaling factor, if you will. So it's equal to the determinant of q times this integral. And so this integral is over any tile. This c value here corresponds to any tile. So in the example that I have down here, this would be C, this would be a tile. You'll notice, for example, in 1D, what does this look like in 1D? It's 1 over 2b times the integral from minus b to b. That's a tile in one dimension, right? which we know is the sink of 2bt. So this is the interpolation function that we have in 1D. In 2D, we have a straightforward extension. Instead of the 1 over 2b, what is 1 over 2b? That's 1 over the Nyquist rate, right? That's 1 over the Nyquist rate. What is determinative Q? That's 1 over the Nyquist rate, or the Nyquist density, I should say. Times the integral over a tile. So we're integrating over a tile instead of minus b to b. That's the one-dimensional tile. Times the Fourier kernel. So that's the multidimensional Fourier transform. We didn't go through a lot of the details in painstaking granularity, but hopefully you have now a good understanding of what it looks like and how it generalizes from the one-dimensional case. Any questions on this? Now here's one thing which is interesting, and are you ready? This is a tile. Now we ask ourselves in this first stage, what are different ways this tile can be used to fill up the U1, U2 plane? First of all, notice that a tile cannot be anything. It has to be something which you replicate and it fills out the entire plane. So it has to be a rectangle or a hexagon or even some of those weird shapes that we talked about before. Well, here's the interesting point, is that there's a bunch of ways to do it. We could replicate this tile in this fashion, couldn't we? We could replicate the tile in this fashion. Now notice here what we do, we're kind of like laying bricks, right? Each different layer is a little bit out of phase with the one prior to it. Yet it does allow for a periodicity vector. Here the periodicity vector is just rectangular. Here it's different. These are the periodicity vectors here that allow for the periodic replication. And over here we even have different periodicity vectors, don't we? So this is an example of a rectangular support and 3 different sets of periodicity vectors that will achieve the Nyquist density. Now what's interesting is that each one of those is a possible replication that we can use. Now what does this tell us? This tells us a value of P. And from this, from the P, we can get the sampling matrix, right? From this value of P, we can get the sampling matrix. So for this value of P, the sampling matrix is going to be rectangular. It's just going to be something like this. This is T1 and T2. Because it turns out if you're rectangular here, you're going to be rectangular in your time domain also. So this is the corresponding Q for this one. Now over here, what we're going to have is we're going to have a different sampling matrix. And I believe that well, the sampling matrix here is going to be a little bit different. I think it's going to be something like this. you're going to have this sampling matrix. You see, this is going to be a different Q. If you have a different P here, where this is P1 and P2, you're going to have a different Q. In a similar fashion over here, you're going to have yet another Q matrix corresponding to this sampling geometry. So the point is, and here's the bottom line, for a given support for your zeroth order spectrum, there are a number of different ways to sample at the Nyquist density. Each one of these has the same Nyquist density. You can sample in this rectangular way. You can sample this way, in which case the spectrum is replicated by these sideways bricks here, or you can sample over here where we have just kind of the bricklayer sort of way of doing things. So the interesting thing is that the sampling geometry at the Nyquist density the geometry of the sampling can vary for a given spectrum, and you can still maintain the Nyquist density. There is not a unique sampling geometry that gives it to you. Here's the point again. Each one of these has a different periodicity matrix. All of these take the zero order spectrum and replicate it differently, correct? And each one of these has a different value of P. This is a different value of P. This is a different value of P. This is a different value of P. Why do we know that? We know that because the P1 and the P2s are different, correct? Each one of these P's has a corresponding Q. That Q dictates the manner that we sample in the time domain. Each one of those P's has a different Q, and the Q dictates how we sample in the time domain, in the T1, T2 domain, if you will. I'm using time in a very general sense. And so for this value of P, we're going to use this sampling geometry. If we use this value of P, we have a sampling geometry that looks like this. I don't know if I got it exactly right, but it's something like this. And over here, we have a different value of a sampling geometry for this P, which is different than the other two P's. So each of these is a valid way to sample the signal at the same rate. And what is common between all of these P's, between this P and this P and this P? They all have the same determinant, don't they? Right? They all have the same determinant. So therefore, they all have the same Nyquist density, because the Nyquist density is the determinant of the periodicity matrix. Now, there's also other cells other than the rectangular cell. Here, for example, we have our old friend, the hexagonal replication, correct? Now, you can see if we have the first cell, I'm sorry, I'm calling it a cell. I should be calling it a tile. If you have a hexagonal tile here, then what would the inverse Fourier transform be? Well, it'd be like the homework problem, wouldn't it? It'd be the inverse Fourier transform of a hexagon, which would be, I think we called it a hink, right? So that would be the reason that you want to derive the hink in order to get the interpolation function if you had a tile which was a rectangular, a hexagonal replication. But even notice here that if we had this periodicity matrix, see, this is a P1 and a P2. In the previous slide, we showed that we can mess around with the P1s and P2s. Here's something else which is interesting. Even for a fixed P1 and P2, you can have a bunch of different tiles. You can have a bunch of different tiles, as we'll see next. For example, we could use this tile, say that our spectrum was 0 outside of a circle, okay? Much like the pennies were here. We could replicate that frequency domain in this hexagonal replication. We could also replicate it in this hexagonal replication, couldn't we? And we would have different values of P1 and P2. So here we would have a value of P, let's call it P sub 1. Here we would have a different value of P, we'll call it P2. And P2, this periodicity matrix, is not going to be equal to P1. Of course, they're going to share the same magnitude of the determinant, aren't they? And notice that this replication has the pointy side of the hexagon on the right and left. This replication has the pointy side of the hexagon on the top and the bottom. And both of them are viable replications of the spectrum when the spectrum is 0 outside of a circle. Just like there's more than one way to pack pennies. And these would both give us a different Q. They both would give us a different sampling geometry. And then it even gets more sloppy. This is very interesting. Let's suppose that we had rectangular circles that were rectangularly stacked. This has a sampling distance of 4w squared. Now, what I'm assuming here is this is 2w, and this is 2w. So the two periodicity matrix vectors are what? P is equal to 2w0. That's this periodicity, correct? And then 0, 2w. So this is the P1. And this is the P2. Is that okay? So the sampling density is this way. Now, we mentioned in information theory and other places, we might like to pack these circles as closely as we possibly can. And if we pack them more closely, we're going to get a smaller sampling density. In fact, we get the Nyquist density by packing them as close as we possibly can, such as here. Now here, let's see what we have here. We're going to have this result. By the way, there's the assumption here that the diameter of the circle is 2w. So we're going to have a P1 here and a P2 over here. And again, in choosing your P1 and P2, you're kind of seeing where the origin here is here. Well, that's the center of the circle. So you want a center of a circle here. Well, that's at this point. And you want the center of the circle over here, and that's at this point. So if we look at that, here's what the periodicity matrix is. I believe I have this upside down. W and minus W. Yep. Yeah, I have it upside down. Actually, the periodicity matrix that we have here is going to be right? Because we go out further. What is the cube root? What is the cube root or the square root of 3? It's like 1.7, right? So we got 1.7. So sorry, this is wrong. Is that okay? So we go out here. No, that doesn't look right either, does it? Well, what's going to be the hypotenuse here? The hypotenuse is going to be 2w, right? Since we're going out 2 radii. And so
I think the problem with the first matrix was that the which sign was flipped. Should have been the lower right element rather than the upper right element.
no, I think that this is root 3w. Yeah, no, this is right. We go root 3w here, and then w here. We go the radius of a circle up, correct? Okay, I'm sorry. So the second value here is the radius of the circle, which is w. So it's root. Okay, so this one is correct. But the beautiful part here is that both of these have the same determinant, don't they? It's 2 root 3 w squared. Okay, the bottom line is we have this result and we have this result. And what we would like to do is look at these, and we notice that we're packing the circles on the bottom a lot more closely than we are on the top, aren't we? We're packing them much more closely on the bottom as opposed to the top. So therefore, the sampling density corresponding to the bottom should be a lot smaller than that on the top. The sampling theorem on the sampling up here is going to be a lot larger because the spheres are not packed as tight as they could be. So what's the ratio of that? Well, it turns out if you take this divided by this, you get 0.866. So it turns out by going to a hexagonal sort of sampling, you reduce your number of samples by about 87%. The hexagonal packing reduces the number of samples that you're going to have to take by 87%.
Oh, I thought that was, you multiply it by 0.866. So
yes, if we do
like 13%.
No, I think this is right.
I think he's saying that it's making it 86%, not reducing it by 86%.
Oh, it's okay. You're right. You're right. I used the word incorrectly. Yes. Okay, it's 86% smaller. So isn't that interesting? Now, what do you think happens if we go to 3 dimensions? Do you think we're going to get a greater reduction than 86% if we go to 3 dimensions, as opposed to if we take the bowling balls and we stack them up so that they're maximally packed, as opposed to arrange them in a 3-dimensional rectangular grid? What do you think happens? Well, it turns out, interestingly, that it really gets incredibly crazy. This is a plot and a table of what happens is you maximally pack spheres in higher and higher dimensions. So you'll notice in 1 dimension, well, nothing happens. We said that this was about 87% here. If you have 3 dimensions, it reduces by 70%. And if you go all the way up to 8 dimensions, it reduces it to 6.2%. Wow. So I think you can see, at least in information theory, where they do sphere packing, that the sphere packing, as tight as they possibly can do it, is a lot better than just replicating spheres in a rectangular grid. We want to pack them as closely as we possibly can.
Now that's interesting, because that picture of bowling balls or cannonballs, from one perspective, the balls were arranged rectangularly.
Were they? If they were, that was not good. I don't know if that's in this this sequence. No, that's not in this sequence. So that's no good. Yeah, I'm assuming that the bowling balls in one dimension, if we just look at a slice of the bowling balls, they're hexagonal. The stack on top of them is also hexagonal, but shifted over to fit in the gaps of the sequence of bowling balls right to the right below it. So this gives some very interesting perspectives. Let me ask you this. Suppose that we had and this is one of your homework problems, suppose that we had a spectrum that was 0 outside of a equilateral triangle. In order to figure out the Nyquist density for this, you would have to figure out how to replicate this triangle in a fashion that the triangles in the replication were as close together as possible. Now, to me, the answer isn't really clear. I think that the best that I could probably do is something like the following. I tell you, it's hard to look at your screen and then draw off the screen. Okay. Oh, that wouldn't do it either, would it? I think it would be something like this, right? I don't know the answer to it, but my intuition says it would be a replication that looked like this. Notice that for some geometries of the spectrum, there is no way that you could replicate the spectrum without gaps. I mean, right here, we're going to have a gap, right? We're going to have a gap here, a gap here. And that's kind of wasted bandwidth. And we should be able to gain it. There should be something that we can do to take advantage of those gaps. There's one final observation that I want to point out to you, which is really interesting. When we do a Fourier transform, you can think of the Fourier transform, and you do this with DFTs also. You can talk about, for example, the Fourier transform with respect to T1. In other words, you take every slice here and you do a Fourier transform on it. Is that okay? And so notice that this is a function of T2 and T1. Over here, we have a function of T2 and U1. So in other words, the T variable has been transformed into the U1 variable because each slice of this has been Fourier transformed. And then what we would do is we would do a Fourier transform in the second variable. and we would get the corresponding spectrum, which we assume is band limited. Is that okay? I mean, we can do this straightforwardly. This is the integral of T1. Let's see, which one did we do? T2. I've simply taken the two-dimensional Fourier transform and taken the kernel and divided it. Since it's e to the j, I can break it up into the product of two parts, right? What is this? This is the Fourier transform of a slice for fixed T2. You can think of T2 being fixed here. So you fix T2 and you take the Fourier transform of the slice, the one-dimensional signal, and this turns out to have this spectrum. And we do that for every one of the horizontal slices. And we get this function. And then once we get this, we can take the Fourier transform of this in the other direction, which is going down, and we get the corresponding spectrum, which is shown here. Now we can go backwards too. We can take this result and we could do an inverse Fourier transform with respect to U1. So notice this is U2 and this is U1. I'm sorry, U2. U2 stays U2. U1 goes to T1. And so we're taking the slices here, and the inverse Fourier transform of this slice is equal to this slice. So anyway, we can define it up. We can define it this way. The interesting result is that if I take the Fourier transform of something finite, if I take the inverse Fourier transform of something finite, it's going to have infinite extent over here. So each of these functions is going to have infinite extent. The consequent of this is very interesting. It says that every horizontal slice, this is a one-dimensional slice of the Fourier transform. This is going to have a bandwidth, and that bandwidth is determined by this. This one-dimensional slice is going to have a bandwidth, and that bandwidth is determined by this. And each one of those one-dimensional Fourier transforms is going to have exactly the same bandwidth. I think that that's fascinating. Every one-dimensional slice of a two-dimensional function, a two-dimensional band-limited function, is going to have the same bandwidth. Every parallel one-dimensional slice of a two-dimensional Fourier transform is going to have the same bandwidth. So take a look at that and see if you can understand it. And if not, we can talk about it some more next time. So with this, I'd like to open up the next topic that we're going to do. And I think this is the most fun of the topics that we would talk about in this class. This is something called POX. Some of you have taken Dr. Schubert's class in tomography and have heard about the ART sort of technique. Who's taking Dr. Schubert's class? Okay, just only Glauco. Okay, we'll discover this. POX is a technique for signal synthesis and analysis that you can apply to things such as missing sensors. You can apply it to tomography. You can apply it to oncology. You can apply it to tomography, reconstruction of three-dimensional images. Remember the radon transform? I'm going to show you an interesting way, another interesting way of doing the inverse radon transform, not using all that weird math, but using the concept of Pox. It is incredibly powerful. Its use is ubiquitous. Where you can use it is in a lot of places, but you shouldn't force fit it into any use. There are certain places where it just doesn't work very well. So that's going to be the topic for next time, and we're going to end up the class doing Pox. And here is what we're going to do. We're going to talk about, I'm first of all going to appeal a lot to your intuition, because there's lots of great intuition that you can get by looking at Pox. By looking at Pox and viewing it as a geometrical operation. So we're first of all going to look at it in a very intuitive fashion. And we'll look at the idea of convex sets, projections, and then Pox. And then we'll look at different applications. And some of these we'll gloss over quickly, others we'll spend a little bit more time of. The Popoulas-Gershberg algorithm, neural network associative memory, resolution at sub-pixel levels. This one is interesting. Imagine you have the world's worst camera, okay? This world's worst camera takes terrible images. I'll explain them in a minute. We'll look at radiation oncology, JPEG and MPEG repair, looking at missing sensors, and then we'll look at a generalization of alternating projections into the area of ambiguity function, synthesis, and Gershberg-Saxton. And so Gershberg-Saxton, for example, was an algorithm which was used in space when the Hubble telescope first went up, and they found out that they had a design flaw in the mirrors. And they used the Gershberg-Saxton algorithm to correct this flaw in the Hubble telescope mirrors. And we'll discover exactly what they were doing there. Currently, in Dr. Bayless's work, we're using the Gershberg-Saxton algorithm to synthesize radar signals with certain interesting properties. So this will be a very interesting area. And so what do I mean by sub-pixel resolution? Imagine the world's worst camera, and this camera has a aperture like this, and imagine an aperture this big, trying to take a picture of me over the whole screen. And this camera is so bad that it only can take one value. It just has one photo sensor behind it that takes whatever light is incident and integrates it, and that's the value that you get out for the camera. So one number. That's pretty bad, isn't it? Is there a way, if we can move that pixel around, say, take a picture here, one number, one number, one number, one number, one number, one number. Is it possible? Uh-oh, thank you. David said my beard is rubbing on my microphone. Could you hear it? Okay, you guys got to tell me this, okay? I'm not used to this. Is the first time in my life I've had a long beard. So I'm still having maturation problems. So can you take all of these individual pictures with the world's worst camera and reconstruct a very detailed image of me? What do you think? Yeah, you can. And one of the techniques to do that is with Pox. One of the techniques to do that is with Pox. And we'll find out a number of, I hope, very, very interesting applications using Pox. Okay, any questions at all? Okay, how many more lectures do we have? Anybody counting? 5 more lectures. Okay, okay. So I will, give you the homework, and we'll talk about the homework next time, and we'll see where that goes. Okay, thank everybody. Yeah.
5, including this one.
Yes, including them all. I omitted one last time, but we didn't talk about the homework this time. So that's fair game for next time. Okay? Okay, I see that everybody is happy with my decision. So we'll go ahead and end it for today. Thank you. Thanks everybody for your attention. Bye-bye.